For standard 14, we're going to step back into working on solving trig equations, but we're going to look at equations that are a little more complex in nature than the ones that you saw back in standard 12. Right? So in example 1 here, we've got multiple trig functions within the same equation. So I want you to pause the video and think about, get creative here. I haven't shown you how to do anything like this yet, but get creative and experiment with ways that you might be able to figure out what values of theta will make the left side equal 0. So after you hopefully giving it quite a bit of thought and trying some things, let's see if we kind of arrive at the same conclusion here. Anytime I have something equal to 0, and just as an example here, let's say I have like 2x plus 4x squared equals 0. One of the things I would notice here is that I have common factors between the two. So, I might pull 2x out, which would leave me with this. And then anytime you have that situation where you have something times something equals 0, then you can set the individual factors equal to 0. So, I might try to do that. So x equals 0. And here, I'd also get x equals -1/2. So do we have something like that here? Well, yes, we do, right? We have 2 and 4. We have sine of theta is acting like our x. So maybe we should try to start by pulling 2 sine theta out of these two terms. And what am I left with? Okay, well, just a 1 in the first term. Then I would have 2 cosine theta in the second term. So I've just factored this left side, and then if the product of two things equals 0, then either this factor needs to be 0 or the other one does. So I can set this to 0. So sine theta is 0, and of course on the unit circle we know that that's happening at 0 and pi. So every multiple of pi, is going to allow this thing to be 0. But on the other hand, this could have been 0, right? I could have set 1 plus 2 cosine theta equal to 0. So we're going to subtract 1 from both sides, and then divide by 2 on both sides. And then, we can do the same sort of analysis, right? Where on the unit circle does this happen? Well, here's -1/2 on the x, so that would happen here and here. So that should make me think of 2 pi over 3 and 4 pi over 3. So I see that theta could equal 2 pi over 3, of course, plus 2k pi, multiples of 2 pi, or theta could equal 4 pi over 3 plus 2k pi. And so putting all of these together yields my entire solution set. Okay, so theta could be lots of things in this equation in order to make the left and right sides equal to each other. All right, so let's take a look at example 2 here. And again, I'd like you to take some time on your own to try to problem solve this. How can you figure out what sign should be in order to make the left side equal 0? So at first glance, you might try the same thing as the last problem. You have sign here, you have sign here, but there's no sign in this term, so you can't do any factoring out of a common factor from every term. But then hopefully what this kind of reminds you of is something like this, x squared minus 2x minus 3 is equal to 0. Okay, well, if I saw something like this, then I would probably factor it just like that. Right, so x equals 3, x equals -1. All right, so maybe we should try that where instead of x, we're just using sine. So I could factor this as sine theta minus 3 times the sine of theta plus 1. And then I could, test what I just did there. Sine times sine is sine squared. The outside, sine times 1, plus the inside, -3 times sine, gives me -2 sine. And then -3 times +1 is -3. All right, so then we can, like on the last problem, set the two different factors equal to 0. So this one would mean that the sine of theta would have to be 3. Now let's pause for a moment. Can it ever be the case that the sine of theta equals 3? Remember that the sine, right, is the y value on the unit circle. And the unit circle only goes up to 1 and down to -1. So the y value could never be 3. That's way up here. So what this means is that this has no solution. This, now not the whole thing, but this part of it has no solution. Okay? So basically we just hit a dead end there. And that's okay. So now we move over to this one. So in other words, this will never be 0. Okay, but maybe this can. So the sine of theta plus 1 equals 0. The sine of theta equals -1. Okay, so when does that happen? So that happens at 3 pi over 2, right, down here. So we can say theta is equal to 3 pi over 2, and then of course plus copies of 2 pi. All right, so one more example, and then you'll get a lot more practice with this in the video notes as well that follow these. So here we have another quadratic. Now, if you were to encounter this, but without cosines, if you were to encounter 2x squared plus 2x equals 1, if you see a quadratic, most of the time our strategy then would be to get one side equal to 0, right? So I think that's a good first step here. So we'll say 2 cosine squared theta plus 2 cosine theta minus 1 is equal to 0. All right, so we might look at this and say, all right, can I factor it? No, probably. If you try, you really can't. You could try a number of different options for how to factor this, like in the last problem, but it doesn't work. But remember, with one like this, you wouldn't sweat it if it didn't factor out. You would just say x equals -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. You do the quadratic formula. Well, we are certainly allowed to do that as well. It's just that the cosine of theta, that is our x. So I would say something to this effect. Cosine of theta is equal to, well, I guess what I just wrote out, -2 plus or minus the square root of 2 squared minus 4 times 2 times -1, all divided by 2 times 2. So inside of that square root, I get 12 over 4. And so then I can do a little simplifying here. This will be the cosine of theta is equal to -1/2, so 2 over 4, plus or minus the square root of 12 over 4. Okay, so I think it's worth at this point separating this out. Okay, so on the one hand, the cosine of theta can equal -1/2 minus the square root of 12 over 4. Okay, but if you type that in your calculator, what you're going to find is that it is smaller than -1. So that ends up being about -1.37. So remember, the cosine can never be smaller than -1. So this does not lead to a solution. But that's okay. We had the same sort of thing happening with one of our factors in the previous example. So we just don't worry about that one. This other one, however, cosine of theta is equal to -1/2 plus the square root of 12 over 4. That is okay. -1/2 plus the square root of 12 over 4 gives you about 0.366. So that one's okay. That's between -1 and 1. So I can go ahead and say, well, then theta is equal to the cosine inverse of this. I'm using cosine inverse because this is certainly not a special value, plus 2k pi. But also, theta could be 2 pi minus that, or the negative of it. You can say it either way, I suppose. I think in a lot of the examples I've done so far, I've always picked 2 pi minus the first angle. But remember, right, if that's 0.366, right, here it is. This is the one I'm finding right now. That's this one. This one is either 2 pi minus that much, or it's just the negative of it. So I'm just going to go ahead and say it's the negative of it, because we weren't told we had to get like the positive answers or anything like that. And so now I'm ready to type that in my calculator, and the calculator spits out theta being equal to 1.196 plus 2k pi, or theta equaling the negative of that. I guess it's approximate, right? It's approximately equal to -1.196 plus 2k pi. So these last two problems that we just did are what are known as quadratic in form. So you can try to factor them, you can try to use the quadratic formula, and then just know that you're setting that trig function that's taking the place of your x equal to that quadratic formula, and then continuing on your solving process from there.